Hello again. We're talking in this session about research design in physical geography, and specifically I've been talking about hypothesis testing. In this video I just want to give you a nice simple example of a piece of research that used a hypothesis testing approach. This is actually a bit of research that I did 30 years ago. It's not necessarily groundbreaking research that you need to be familiar with, but it's a nice example to use for this session because it very clearly follows that hypothesis testing approach that I described to you in the last video. And you'll remember from last time we said that research following this kind of approach begins with some kind of problem in the real world or some kind of controversy in the literature that gives us a question. And answering that question is then the aim of our project. And I think in the last session I used the example of why a soil might be red, and we said, well, that's our question. Why is this soil red? And once you have a question, you then have a number of possible answers, and hypothesis testing is all about figuring out which of those answers might be valid and which of them definitely isn't valid. And each of those possible answers is a hypothesis, and those hypotheses are what you're going to test by looking at evidence. So for the red soil example, I think we said, well, one hypothesis could be that there's iron in the soil and it's the iron that gives it the red colour. Well, once you have a hypothesis, that then carries with it predictions of what you would expect to find if that hypothesis were true. So if it were true that the red soil was because of iron in the soil, well, then you would expect to find some kind of correlation between the soil colour and the soil composition in terms of its iron content. So there's a prediction that follows from the hypothesis, and that prediction opens up for you a test that you can carry out. If you go out there and you find that there's no correlation whatsoever between the iron content of the soil and the colour of the soil, so it isn't that the red soils have more iron in them than the not red soils, that falsifies your hypothesis. So the nature of the test tells you what observations you need to go and make. So this hypothesis testing approach is kind of leading you step by step through the research. So we know that we need to go out and we need to find some red soils, and we need to look at the chemical or iron composition of those soils, and maybe get some non-red soils and look at the iron composition of those, and then see whether there's some correlation between the iron and the colour. Now, we also made the important point last time that a correlation does not necessarily imply causation. So even if there is a correlation, that doesn't necessarily mean that you've verified your hypothesis. But if there isn't a correlation, well, then you have falsified your hypothesis. And if you want to remind yourself what we were saying about verification, falsification, inductive, deductive logic, critical rationalism, Karl Popper, and hypothesis testing, go back and look at that previous video. Because what we're going to talk about this time is just a specific example of a project that has gone through that process and arrived at a very straightforward conclusion, testing a particular hypothesis to do with a particular question. Now, this piece of work, 1989, Stacking of Basal Debris Layers in West Greenland, published in the Journal of Glaciology, it was actually something that emerged from my PhD research. It was just one small part of my PhD. So it's a very constrained, a very confined, very limited piece of research with a very simple question, a very straightforward methodological approach, a very straightforward research design, leading to a nice straightforward output. So look at this as an example of the kind of research that follows that hypothesis testing approach. So to begin with, just a word on background to the topic of that paper, basal ice. What is that? Well, in a glacier, most of the ice in a glacier is formed by snow falling onto the surface. We call it meteoric ice, and it builds up layer upon layer. But right at the bottom of a lot of glaciers is a layer of ice which has been affected by the contact of the glacier with its bed, and it has a different chemical composition, a different physical composition, often characterized by having lots of debris in it. And in that photograph there, that's the basal ice layer on the volcano, the ice cap of the volcano Cotopaxi in Ecuador, and you can just about see in the top left hand corner of that picture is some regular meteoric glacier ice formed by the compression of snow crystals under their own weight to make ice. But then the bulk of the photo is taken up by a section of the basal ice layer, which is the bottom part of the glacier, which has been interacting with the bed beneath it and has somehow picked up or entrained a lot of debris, making that ice look very different from the cleaner ice above it. So end-glacial ice, or the meteoric ice that occupies the bulk of a glacier, is typically relatively clean. There'll be bits of atmospheric debris going into it, but there won't be much debris picked up from underneath. And in these pictures taken from the Russell Glacier in Greenland, in the bottom right hand side you can see a little bit of ice that I've chipped out of the glacier, and you can see it's bubbly, but it doesn't have much debris in it. And all the way through the thickness of the glacier at this particular location, there's clean ice right the way to the bed. In the top right hand picture there, it's a fairly unusual situation really, to have clean end glacial glacier ice going all the way down to the glacier bed, and there's no evidence of any basal ice in those pictures. But in many situations, glaciers do have a basal ice layer, and these photos illustrate what that's like. So in the bottom photo here, again, I've chipped a little bit of ice out of the glacier, and you can see a big difference from the previous slide in that the ice here doesn't have the bubbles in it, so it doesn't have that white colour caused by all the bubbles in the ice, and it does have lots of debris in it. And in the photos above, you kind of pull back a little bit from the front of the glacier and look at the basal ice layer. It's typically full of lots and lots of debris within the ice. And we can separate out different facies or different types of basal ice in which the characteristics of the basal ice are a little bit different because of the different processes by which the ice has been formed, the different mechanisms by which debris has been entrained into the ice, for example, or whether the ice has been formed by melting of ice and then refreezing of water to make new ice. All these different processes operating underneath the glacier create different types of ice in the basal layer. And we often distinguish, for example, between the stratified facies, so-called because it's made up of layer upon layer of clean ice, dirty ice, clean ice, dirty ice. There's another facies called the dispersed facies, where debris is dispersed, scattered through relatively clean ice, but with these aggregates or clots of debris dispersed throughout it. Also common are these features called debris bands, where a line of debris cuts through otherwise clean ice, and sometimes, as in the bottom photo there, you get a whole stacked sequence of these debris bands at the margin of the glacier or at the base of the glacier. And this work that we were doing in Greenland back in the 1980s, that this paper that we're talking about today relates to, was looking at what we refer to as stacked sequences of different basal ice facies making up the whole of the basal ice layer. So here there's a figure at the bottom left for scale in this picture, and then I've labelled right at the bottom there's about a metre or so of that stratified facies. Then there's a series of debris bands, and those debris bands are cutting into the bottom section of the dispersed facies. So those facies that we mentioned in the previous slide, here they all are occurring in sequence, stacked one on top of the other at the edge of the Greenland ice sheet, where we're looking at the bottom of the glacier. So that's the topic that this research was focusing on. And the controversy in the literature was, well, how do we get these stacked sequences of different basal ice facies? And in these next few slides I've put some quotations from the paper just to show for you how directly we were following that process of saying, well, there's a controversy that gives us a question, and our aim is to answer the question. We'll have a hypothesis, we'll develop a test that will include predictions, we'll go and make our observations, and then we'll compare our observations with the predictions to carry out the test of the hypothesis to say whether it appears to be valid or whether we can falsify it. And we were very explicit about that in the paper. And from your point of view right now, that's a useful process to go through as you develop your own projects, perhaps for your dissertation next year. Just be very conscious of your thought process as you go through each step. So here, when we wrote the paper, we said, various mechanisms have been proposed to explain the development of vertically stacked sequences of different basal ice facies, but despite a plethora of theories and counter-theories, few critical tests of specific hypotheses have hitherto been carried out. So basically, lots of people had lots of ideas, but we hadn't really tested them out to find out which ideas were good and which ideas were bad. Well, there you go. There's a great starting point for any project. We've got lots of ideas, but we don't know which of them are any good. Well, straight away you're in with a reason to do some research. So our aim, therefore, following very logically from that, and that's the point I've been making throughout these sessions, that once you get into a research design, the stages kind of follow naturally from each other. So once we have that controversy or that uncertainty, all these untested theories, well, our aim, obviously then, is going to be to take at least one of those. Our aim is to test one of the competing theories of base ice formation, to find out whether, and here we just pick one of the existing theories, to find out whether the base ice sequence in Greenland is really created by this process called freezing on, which a paper by Weertman in 1961 had suggested. So that's what we're trying to do. And we said that very, very straightforwardly in the paper. In this paper, isotopic evidence is used to test this simple freezing on hypothesis. Now what we're talking about there is that this chap Weertman said that at the bottom of the glacier, if there's water flowing along, then in certain situations that water can freeze. Here's a glacier, the water can freeze at the base of the glacier, building up layer upon layer of new ice, frozen on ice. Sometimes it might be relatively clean if there's not much debris available and lots of water freezing. In other situations it will be very dirty if there's not so much water but lots of debris. So he's imagining the subjacent accretion, the sticking on the bottom of these layers of clean and dirty ice. And that's his theory for how the base ice sequence is created. Our aim is to go and test that theory. Straightforward. We don't know how it's formed. This chap says it might be like that. Well, let's go and have a look. And we're going to use the stable isotope composition of the ice to try and figure that out. So what's the hypothesis then? And already you know this because I say everything leads on step to step. So Weertman, 1961, proposed this freezing on mechanism to explain the debris band stacking of the clean and dirty layers in the sequence. That's what we said in the paper. In other words, what his hypothesis says is that all of the base ice, including both the bands of debris and the cleaner layers in between those bands, what we now call the dispersed facies, and the stratified facies by implication, but basically all the base ice is created by the freezing of meltwater underneath the base of the glacier. So you've got liquid and it freezes. That's his idea. Now, at the time he said that, we didn't really have the technology to check that very easily. But because of the way that stable isotope glaciology emerged through the 60s and right through into the 80s, by the 1980s, co-isotopic analysis, a particular chemical analysis that we can carry out on the ice, enables us to tell the difference between ice that was formed by the compaction of snow that fell out of the sky, meteoric ice, and ice that was formed by the refreezing of liquid water. So we now have this test that can discriminate between snow ice and water ice. And that's important because once we think about the Weertman hypothesis, we can think about the prediction of the hypothesis. So, well, if Weertman's right, what would you expect to see in that glacier? If it's true that all the base ice is created by freezing of meltwater at the bed, not by all sorts of different processes for all the different facies, but freezing of water at the bed gives you the whole lot. Well, as it says there, and this is what we said in the paper, this freezing on hypothesis carries the specific prediction that both the debris bands and the intercalated layers of clean ice will be formed of ice frozen from water. So that's the implication of Weertman's theory. So it isn't going to be a layer of refrozen water and then a layer of normal glacier ice and then a layer of ice formed from snow. It's all going to be frozen from liquid water. So that's the prediction that follows from Weertman's hypothesis. If Weertman was right, then that is what we would expect to see. So now it's giving us the observations that we need to go and make. We obviously need to go and look at those different types of ice and see whether they're formed from frozen water or from compressed snow. So that's our test. And we said in the paper, well, Juzel and Souchet in 1982 presented a model whereby refrozen ice could be distinguished from fernification ice, that's the meteoric snow ice, could be distinguished from fernification ice on the basis of its composition in delta D and delta oxygen 18. So basically there's this test that Juzel and Souchet developed that enables us to tell the difference. So what we're saying there is if Weertman was right, the isotopic signature, the isotope chemistry, just think of it as chemistry if you don't know much about the isotopes, the chemistry of the water for both the debris bands and the clean layers should have this water freezing signature, not a precipitation and compression signature. So we now know exactly what we need to go to look for and what we would expect to see if the hypothesis was right. And if we don't see that, well then that will tell us that the hypothesis isn't right then, because we have to see that if the hypothesis is correct. So we've set up this very simple project where there's a hypothesis. If it's true, we'll see this. If it isn't true, we won't see that. We can now go out and look and see whether we do see it or if we don't see it. So off we go, and here's a picture of me thurtling about underneath the glacier 30 odd years ago during my PhD, I think. But we basically did this. We went and crawled around underneath glaciers, sampling the ice, and sent our samples off to the lab to get the isotope signature, the chemistry of the ice figured out, so we could see what kind of ice we were dealing with for all the different layers through the basal ice sequence. So we made our observations, and there in the paper it says, well, here are our observations. And that's what you do when you do your research. You set out your research design, you set out your methodology, you say where your field area is, you explain what you're going to do, you go there, you do it, you collect data. And this is just saying what the data was that we collected. So we've got samples, analysed them for oxygen-18 and deuterium, and it says our results were that the results discriminate clearly between two distinct sample populations. The cleaner basal ice layers, well, they seem to be basically meteoric ice. They were originated from snow that got compressed, maybe was modified in some way in the basal layer, but it hadn't frozen from liquid. But the debris bands, the really dense, dirty bits, they were non-meteoric. That wasn't just stuff that had fallen out of the sky, it was stuff that had refrozen from liquid water at the base of the glacier. So the different facies within the basal ice sequence are being created by different processes, and we know that because the ice has different origins. So already now, if you've been listening to what I've been saying and you've been following through this project, as soon as you see those results, as soon as you, well, literally in my case, 30 years ago, ripped open the envelope from Denmark and said, here are my isotope results. Well, they're different. Straight away now you should be able to figure out what you think of Weertman's hypothesis, that it was all created in the same way, now that you can see that the different basal ice facies have different signatures in terms of their origin. So there's our conclusion, and it's easy to arrive at the conclusion once you've got the data, the observations, given that you've set up this hypothesis testing approach and you understand what the predictions of your the predictions of your hypothesis were. So the evidence supports the proposition that the debris bands are entrained by a freezing process, liquid freezing at the base of the glacier. But Weertman's hypothesis, which was that freezing on of both clean and dirty ice was happening, well, that can't be sustained because we just saw that the clean ice layers are meteoric, the debris bands are frozen on from below. So some of the basal ice is created by that mechanism, but not all of the basal ice. So Weertman's hypothesis that all of the basal ice was formed in that way, well, we falsified it in a very straightforward kind of a way. So the key points from that example, go and have a look at the paper and just see how it expanded out into a full paper, and just make sure you understand the logic that we were going through. So you don't need to worry about studying how the basal ice layer works or what the stable isotopes are all about, but just understand the method that we followed in terms of hypothesis testing. And the key points to take away are these. There was a beginning in the literature. People had been working on this previously, they'd come up with lots of ideas, but there was controversy. People hadn't yet sorted out which ideas were good and which ideas were bad. And that led us to a question, well, what is the origin of this sequence? And there was a clear aim based on a hypothesis. Our aim was to test this one particular hypothesis of Weertman 1961. We had a logical method following on from that hypothesis, giving us predictions, giving us a test. We were able, therefore, because we knew what we needed to find to test this hypothesis, we had a method that enabled us to go out and collect data. The data was straightforward, and as soon as we saw the results, that's always a sign of a very straightforward research project, as soon as you saw the results from your measurements, you could apply those back to the original hypothesis and say, this can't be true, this hypothesis can't be right, because look what we've seen. If we'd seen something different, we might have said, that actually fits our hypothesis. And remember, we wouldn't then have said, this hypothesis must be true. We'd have said, we haven't yet falsified this hypothesis. It might still be true. We'll retain this hypothesis for now while we carry on doing further research to keep testing it. And eventually, if we simply can't falsify it, well, then we'll begin to think maybe it could be true. But in this particular case, we did falsify it. And so we moved on and said, well, that's not the right answer. okay, let's now take another of the hypotheses. Based on what we found out by looking at this one, let's take another one and test that, and let's see if we can begin to figure out what is going on. We found out that this isn't what's going on, and that's progress, that's really important, but now we want to figure out what is going on, so that's the next research project. And if you want to get into this literature and follow it through to the present day, you'll see how this subject has moved forward with the science over the years, and that's how science progresses. Testing hypotheses, finding stuff out, having new questions, new hypotheses, testing those, rejecting the ones that are wrong, and hanging on to the ones that seem to work out okay. So that's the end of the case study. Suggested reading I mentioned to you before. There's a chapter 6 in the How to Do Your Dissertations book, which is all about research design, and there's a paper that we've actually just talked about in this session, the case study paper 1989. Go and have a look at that if you want more detail. And what we've done over these 2 sessions is just a summary to remind you of what we've done in the whole of this extended session over a couple of videos. We've made the point that physical geography is a research-based discipline. Everything we know in physical geography we know because people have done research on it. All of that research has been based on different kinds of research design. There are different ways of finding things out. Different ways are appropriate for different kinds of problem. For a lot of problems, the hypothesis testing approach is a good way forward in physical geography. It doesn't apply to you can't use it for everything, but in a lot of situations hypothesis testing is a useful approach. And we said a little bit last time about Popper, critical rationalism, black swans, white swans, all that kind of business, inductive and deductive reasoning. Make sure you get a rough idea of how that works. And if you're unclear about that, go and have a look in the Parsons and Knight Dissertations book. Chapter 6 will explain it to you. Again, but you can have a look at that in your own time. This is really relevant to your degree because you will be doing research projects of your own, and it's important that you understand A, the importance of research design, and important B, that you can apply a relevant and appropriate research design to your own particular research. It's also important because not only for doing your own research, it's important for judging other people's research. If someone's done some research and they say, look, here's my results, this is how I think the world works, you need to look at how they've done it. Did their research design make sense? Remember last time we talked about syllogisms and logic. You need to use that kind of critical approach to see, well, does that conclusion really follow from that observation? Was that the right observation to make, given that this was your hypothesis? Is this the right bit of equipment to use in this environment? There are lots of things that can go wrong doing research. And what I hope we've shown in these couple of videos is that you can work through a method to ensure that you're following an appropriate research design for the particular problem that you're trying to solve, or the particular question that you're trying to answer. Okay, thanks very much.